Hey everybody, welcome back. Today we are going to be talking about intramolecular aldol cyclizations. Now, the best way to get into this is to just flat out talk about it. So here's our molecule. And we treat this, it is reversible, with sodium hydroxide and heat. And here's what we get. Is this product. That's the product we get. Now, if you're looking at that and going, huh? I can't rightfully blame you, because this is kind of a strange one. So let's dig in and take a look. Hopefully by this time you realize base and a ketone will do one of two things. Base with ketone will either give you the enolate, which, believe it or not, is preferred over the hydrate, which is not stable. So we're going to do an enolate instead. Now, looking at this molecule, you can probably take a guess as to what carbon was deprotonated in order to get the enol. So let's take a look here. This is a 5-membered ring, so we need 5 carbons. I'm just arbitrarily going to start 1, 2, 2, 3, 4, and 5. You can see 1 through 5 there. So if we do this, and we enolate to form this, as a reminder, your book and I have a fundamental disagreement on what the structure of an enolate should be seen as. They're fond of leaving the anion on the carbon. I prefer this structure. So now we reform the enolate. We don't have any other electrophile in the system. More on that in a second. So we do a nucleophilic attack and open up the ring. And that puts us here. This would be carbon 1, carbon 2, 3, 4, 3, 4. This would be very poorly drawn. My apologies. 5. Your attachment is there. You've got a methyl group hanging off of it, the unwritten 6. And I'm going to erase that 5 just so I have room to play. My pen will let me. There we go. And the O-. So that's a 5-membered ring. More on why we use the less stable enolate for this in just a second. So let's just redraw this on this page. There's the intermediate we just drew. Here's a water, so it can snag a proton. We're now here. And if you've watched the most recent video that I put up, which was about the alpha-beta unsaturated carbonyl, that this is the next reaction step, and you get this as your product. Every step of this is reversible, but your cyclized product there is usually lower boiling than the big spread out ketone you had before, so it can distill outward. All right, so the next question we have is, why the least stable enolate? Because if you'll look, at this ketone, when you apply a base to this, one of two things will happen. You'll either form the more stable enolate, which looks like this, or the less stable. All right. So the question becomes, why do we use the less stable enolate in our reaction, where the top enolate would be more stable because the alkene is more substituted? Almost said subsidized. Well, the reason for this, let's take a look. If we have this as our enolate, we have this as our enolate, and say we try to do the cyclization here. There we go. Here's what we get. A 3-membered ring. Oh, horror! A 3-membered ring that looks like this. Yeah, that's nasty, folks. That is nasty. The bond angles on this are screaming, just undo me. So it will, this may form, but it will very promptly reverse, and I'm going to hop back a couple slides, and I want to point out one thing. The reason the 5-membered ring works here so well is because on the 5-membered ring, sp3 bond angles are 1099.5. Bond angles on the inside of a pentagram are 107 degrees. So it does not take a whole lot to get this to cyclize into a 5-membered ring, which is a big part of why 5-membered rings are easier to form than 6-membered rings. All right, so we've established that the 5 will work, that the 6 won't. I'm sorry, the 5 will work, the 3 will not. Can we do a 6? Well, let's take a look. At this ketone. And let's start drawing some numbers. 1, 2, 3, 4, 5, 6. Aha! So this could work. And in fact, how this would work, a lot of you will notice that I'm using potassium and sodium hydroxide interchangeably. They are interchangeable. So now the product we would get would be this 6-membered ring. The product would be that 6-membered ring. And if you needed to count the carbons, 1, 2, 3, 4, 5, 6. All right. Now, this is only one example of how this can work. This is just one example. Another example would be something like this. I always have to check and make sure that I have the number of carbons right. So, something like this. Let's do some carbon counting. If we start out here with the CH3, that is 1, 2, 3, 4, 5, 6, 7, 8. Ruh-roh, that's not good. We can't make an 8-membered ring this way. And I'd have to say you're right, but let's redraw this. I think that's right. And now let's draw it with starting here. 1, 2, 3, 4, 5. Aha! All of a sudden, this becomes a possibility. 6, sorry. Even more aha! Now, this becomes a possibility. Because if we flip the page, and we've got this, we remove the proton, we form our enolate. What we get is here. I know I'm running out of time. I get excited. And now if we need to count, and folks, when you're doing these on a quiz or an exam or whatever, homework, don't be afraid to count carbons. You've noticed I've been doing it all the way. This isn't Las Vegas. You can count all the carbons you want. 1, 2, 3, 4, 5, 6. So, pi bond reforms, and the nucleophilic attack occurs like so, opens up, and we're running out of time, and we get this as our final product. All right, this was aldol cyclization. 3 is good, 3 is not good, 4 is not good, 5 is great, 6 is okay, and above that it gets a little ridiculous. Next thing we're going to talk about is the Claisian condensation, where we start working with esters. So, till then everybody, stay safe, stay healthy, stay hydrated.